So we're now going to start talking about the properties of continuous time Fourier series. The first one of which is linearity, as you can see on your screens. Before I talk about the property itself, let me just clarify some notation. So the notation we're going to keep on using for the rest of this chapter is shown here. So what this depicts is if there's a signal x of t, which is a periodic signal with period capital T, the Fourier series decomposition of this will yield Fourier series coefficients, which are denoted by a sub k. So that's a notation we're going to be using. At the same time, for this property, we're saying that there's another signal y of t, which has a Fourier series decomposition, which is given by b sub k. One of the important point to note here is that we're assuming that both these signals have the same period. They're periodic, and they both of them have the same period. Now, the linearity property states is that if I form a linear combination of these two signals, so in other words, if there's a constant a, so there's a times x of t plus b times y of t, this signal is fairly obvious, is also a periodic signal, which has exactly the same period as the individual signals x of t and y of t. And linearity, according to the linear property, this signal, of course, is going to have a Fourier series decomposition. And the Fourier series coefficients for this signal are going to be equal to capital A times a sub k plus capital B times b sub k. In other words, the Fourier series coefficients are also a linear superposition of the individual Fourier series coefficients of x and y. Now, how do you prove this? I'm not going to do it here, but I urge you to try to do this on your own. It should be simple enough, but this proof follows directly from using the analysis equation. So the second property we're going to talk about is time shifting. So once again, let x of t be a periodic signal, which has a Fourier series decomposition given by a sub k's. The question we want to ask is, what if I shift the original signal by an amount which is t0 seconds? What happens to the Fourier series coefficients? How can I relate those Fourier series coefficients of the shifted signal with the original, with those of the original signal, which are a sub k's? Now, it is clear, of course, that if I shift the signal by a constant amount, which is t0 seconds, and the periodicity does not change, the fundamental period does not change. So let me just go ahead and try to determine what these coefficients b's are. So b sub k is, in order for me to determine those, I will only, I'll just use the analysis equation. So b sub k is equal to 1 upon t, integral over one period. For my ease of analysis, let me just take that period from 0 to t. And the signal that I wish to determine the Fourier series coefficients of x is x of t minus t naught. This needs to be multiplied by e raised to the power minus j k omega naught t dt. In order to try to relate this to a's, let me just make a change of variables. So let a new variable tau be equal to t minus t naught, and let me just plug this new variable back into the integral above. So b sub k's, therefore, are given as 1 upon t. This integral, this is x of tau, and this is e raised to the power minus j k omega naught. T is tau plus t naught, so this becomes tau plus t naught, and dt is the same as d tau. As far as the integral limits are concerned, when t equals 0, tau is minus t naught. On the other hand, when t equals capital T, tau becomes equal to capital T minus t naught. So therefore, the integral limits are from minus t naught to capital T minus t naught. Now, this is equal to 1 upon t. Mind you, this integral limits, once again, is over one period, which is capital T. So I can just simply say that this integral is over one period. I have x of tau here. then I have e raised to minus j k omega naught tau t tau, and I can pull up e raised to minus j k omega naught t naught outside because that's not a function. That's not a function of the variable integration variable tau. So what you observe immediately is that this thing here is a subcase. And from this, we obtain the expression that the Fourier series coefficients of the shifted signal, which are b sub k's, as a function of the original Fourier series coefficients, are given as e raised to power minus j k omega naught t naught times a sub k. So that's the relationship between the Fourier series coefficient of the shifted signal with those of the original signal. So let me just, so that's our conclusion. One of the things that you would immediately see is that the Fourier series coefficients, which are b's, the magnitude of those is exactly the same as those of the original a sub k's, right? So that's something that you can try to verify on your own.